So welcome everyone to the Shannon channel. I'm really happy today to have Rashmi from CMU, and she's going to talk about convertible codes. And I think this talk is going to be the last this summer, and then we will resume in September. So I'm really happy to have Rashmi conclude this year's series. Thank you, Rashmi.
Yeah, thanks for this opportunity, Salim. So just a quick question: am I audible enough?
Yes. Yeah.
Okay, cool. Yeah. Hi, Salim. Thanks for this opportunity again to speak on the Shannon channel. And also, thanks for creating this fantastic platform for the community. This is great. Hi, everyone. Welcome. Today, I am really excited to speak about convertible codes and the code conversion problem, which is a coding theory problem motivated from a real-world systems challenge and hence has a relevance to practice. So the coding theory problem that I'll talk about today is a joint work with my PhD student, Francisco Maturana. And the systems motivation that I was talking about comes from a joint work with my PhD student, Saurabh Kadekodi and Greg Ganger. Greg and I are co-advising Saurabh. Okay, so here is the outline for today's talk. I'll start with an introduction and motivation for code conversion. Then I'll move on to presenting convertible codes, which is a framework to formally study this code conversion problem. Then I'll present lower bounds on the access cost of code conversion, which is a particular cost metric for this process. Then I'll move on to presenting achievability results via an explicit construction, which has high field size. And then I'll move on to presenting low field size explicit constructions, and then end with a summary and a discussion of open problems. Okay, so moving on to introduction. So cluster storage systems are the foundation for data-driven systems, and they have enabled this data revolution that we have seen in the last few decades. So these cluster storage systems are typically of large size, typically running into hundreds of thousands, and in some case, like in the case of cloud storage systems, constitute of millions of disks and storing from petabytes and some systems to even exabytes of data. And at this scale, these systems are built incrementally over time as the demand grows. And in these large-scale systems, failures are common. In fact, these are considered, disk failures and server failures are considered the norm rather than the exception. Disk failures in particular are measured using a metric, or it is called annualized failure rate, which is basically the fraction of disks that fail, that are expected to fail in a given year. And in order to ensure that data is not lost and is available, even when such a churn or failures are happening, data is often stored in a redundant manner. When the scale of these storage systems were small to medium size, like a few decades ago, many storage systems used replication, that is having multiple copies of the data as the main form of redundancy. But today, given the humongous scale of the storage systems, most large-scale systems use erasure coding. So let's see how erasure coding gets used in distributed storage systems. So I'll take an example of an n equal to 14 and k equal to 10 code. And I've chosen these parameters because these are the published parameters for the erasure code employed in Facebook's cluster storage systems. So now, since k is 10 in this example code, we'll start with 10 data blocks. And since n is 14, 4 parity blocks are added, which are functions of the data blocks as specified by the code employed. And then this set of 14 blocks are then stored on different disks and typically also chosen from different failure domains. For example, different servers, from different racks, from different failure domains. And this set of 14 blocks together is called as a stripe. in the coding theory parlance, so we can keep thinking of this as the code word. So I'll use the term code word and stripe interchangeably throughout the talk. Okay. So now let's look at what is the amount of redundancy that gets introduced in the systems when one uses codes. So the amount of redundancy that is needed depends on the parameters of the code, which is n and the k used, right? So for example, in N14K10 code, the storage space overhead is 1.4x, right? So while this redundancy provides fault tolerance, it comes with a significant cost, right? So first of all, there is this direct cost of additional hardware resources. There is the number of disks that one needs to buy. In addition, there is also increase in the cost for energy, cooling, physical space, and operations, and so on. Hence, it is crucial to introduce this redundancy in a resource-efficient manner. And in my conversations with system administrators from various companies which have really large-scale storage systems, such as including Google, Facebook, Amazon, and others, they say that even a single-digit reduction in storage space is significant because literally it translates to millions of dollars in costs. Okay, so now let's take a look at how does this redundancy gets configured in storage systems. So the amount of redundancy is chosen to meet two key requirements. So one is durability, and the second one is availability. And these requirements are measured or quantified using some metrics. For durability, a popular metric that is used is what is called as mean time to data loss. So which is basically modeling the system as a Markov chain and then analyzing the mean time to data loss for that model. And availability requirements are typically expressed as some bound on the cost for reconstruction. That is when some data blocks are unavailable, and if there is a read request to that data block, how much overhead is involved in reconstructing that particular data block and serving the read request. And then based on some average measure for the failure rate observed in the disk fleet, the parameters of the code, n and k, are chosen such that the desired values for this durability and availability metrics are met. Thus, the redundancy configuration is really done in a top-down fashion, which is agnostic to where the data actually gets stored and also how these disks actually fail in the real system. So implicitly, the current redundancy configuration mechanisms are assuming that disks fail identically, right, in a similar fashion. So we can say this, the current redundancy configuration approaches are agnostic to failure rate differences among the disks. So we did a study on the failure data of disks from the production clusters at Backblaze, which is an internet data backup company. And we observed that failure rates vary significantly. So here is a plot which shows the annualized failure rate on the y-axis and different disk groups, which are basically different make models that constitute this particular storage cluster. So this is a large storage cluster consisting of multiple tens of thousands of disks. And so these are the different disk groups as shown on the x-axis. And as we can see, there is a huge variation in the failure rate across different disk groups. And there is also variation in the failure rate as the disk ages. It is well known that the variation of the failure rate across time or age of a particular disk family takes this, what is known as a bathtub curve. So in the initial time of the lifetime of disks, which is called as infancy, failure rate is typically high. And then it goes into what is called as useful life phase, where the failure rate is low and pretty stable. And then again, it starts rising up and that is called as wear out, which is on the right side. So this plot that we are seeing here is a textbook bathtub curve. Now let's see how such a bathtub curve looks in the real world. So this is a failure rate curve from the real world production data from Backblaze cluster. And as we can see, even for this disk family, the failure rate curve looks very much like a bathtub curve, right? So there is infancy, useful life, and wear out. And there is significant variation of the failure rates.
And Rashmi, can I ask you a question?
Yes, sure.
Okay, thank you. So suppose that I buy a bunch of disks today, all right? So what can be the source of having different or non-identical, basically, distributions for the failures or behavior, basically? Why can they be different?
Yeah, so very good question. So this is because, so think of the scenario of a large scale cluster operator, right? So let's say Google, for example, right? Or even in this case, right? So system administrators for such large scale storage systems add disks over time as demand grows. So for example, you would buy a bunch of disks this year, and you will see what is the best disk family to buy for your requirement and the price points offered by the disk manufacturers, right? And then next year, you will add another bunch of disks. And that time, maybe you would buy from a different manufacturer because they are cheaper, or maybe they have the capacity and the IO requirements that you need. So it can be from a different disk family, right? So for example, one could be from Seagate, another could be from Western Digital. So these are these make models, that the different families that I was talking about. And they have, as we saw, very different failure rates.
Sure, then we need to change the coding scheme that we have over time as well, right? I mean,
yes.
Then we are...
Very good question. And that's what I'm talking about. And that is where this problem of code conversion comes about.
I see, all right, sure, thank you.
Okay, cool. Okay, so as we saw, the failure rate of disks change over time, and it's also variable across our different disk families, right? Okay, so now let's take a step back and recall that under the current redundancy configuration mechanisms, the implicit assumption is that disks fail similarly, right? So under this assumption, the reliability offered by two stripes, which have data encoded using code with the same parameters, will offer same reliability, right? Because the implicit assumption is that disks all fail similarly. So the picture would look something like this. However, in reality, as we just saw, disks fail very differently. So same two stripes, which have data encoded using a code with the same parameters, in reality offers very different reliability, right? So for instance, depending on the failure rate of the disks where the blocks of the stripes get stored on, the same amount of redundancy may be insufficient in some cases and may be overly wasteful in some other cases. So this brings up the opportunity to tune the redundancy over time as disk families go through different phases of life, especially using a lower redundancy scheme during the useful life phase where the failure rate is also lower and also pretty stable. So this is the case that we made in our FAST 2019 paper, and there are more details in that paper. I'll not go into that here. But at a very high level, in order to tune the redundancy in storage systems, one will have to keep track and monitor how the failure rates are changing over time in production when the system is running, right? And typically, the systems consist of multiple disk families. For example, let's say there are two disk groups, X and Y. So they would have been deployed at different instances of time. They enter end infancy and enter useful life at different instances of time, and they enter wear out also at different instances of time. So let FT denote the fault tolerance scheme used by the default approach. That is an approach that doesn't consider, that doesn't tune the failure rate, redundancy scheme for different failure rates. So in order to tune the redundancy during useful life, what we propose is to use the default approach during infancy and wear out, when the failure rates are highly variable and they are high, and tune the redundancy scheme to the observed failure rate of that particular disk group during useful life. So here, for example, FTX for disk group X and FTY for disk group Y. So in order to do this, one needs to be able to say when to change that redundancy, right? As we observe the system over time, and also decide what redundancy scheme one should use during this useful life period. Okay, these were the questions that we looked at in the FAST 2019 work. And basically, this presents HART, it's a redundancy tuner, the Heterogeneity-Aware Redundancy Tuner, which basically actively engages with the failure data observed in the system, identifies these change points where the redundancy needs to be changed, and also identifies what low redundancy schemes can be used that meets the durability and availability requirements. So I'll not go into the details of this in this talk, but at a high level, I would like to show what one can achieve by doing redundancy tuning. So this is again from the data from the Backblaze production cluster. And here, y-axis is the space savings in terms of storage space that one can achieve if one does redundancy tuning. And x-axis is again different disk groups. As we can see, one can achieve, so there is a potential to achieve 11 to 16% storage space savings by doing redundancy tuning. And as we discussed earlier, this literally translates to millions of dollars. Okay, so by now, it looks like all large-scale storage systems now should be doing redundancy tuning. Right? However, as there was one question earlier, redundancy tuning is not free. So when the failure rate of disk groups change, we need to change the rate of the erasure code of all the data stored on those disks. And often, in order to do such a change, one needs to change both the length n and the dimension k of the code employed. So one might think that we can potentially keep the dimension k fixed and vary only the length. But often this is not possible because there are other constraints on the value of k, for example, from the availability constraint, and also based on how the system is actually configured. So there are some additional restrictions on the values of k. So it's not possible to choose one value of k and then vary n. So we need to change both n and k. Okay, so now if one wants to do that, the default approach to do such a change in the parameters n and k would be to re-encode the data of the disks undergoing this failure rate transition. And such a re-encoding would require reading all the data units and then computing the new parities according to the new code. However, this re-encoding process is prohibitively cost expensive. So this cost of conversion, as we will soon see, is pretty high. And that's because typically in these large-scale storage systems, a large number of disks undergo transition at the same time. And this results in highly varying and large spikes of resource consumption in order to do this conversion. So we are collaborating with Google on redundancy tuning. And here is some data from the production clusters at Google. So on the y-axis here, I have total I/O per day as a percentage of the, so percentage of the total cluster I/O bandwidth that is consumed, that will be consumed for just for conversion if one does redundancy tuning. Right? So basically, you can think of the y-axis as the cost of conversion if one would do redundancy tuning, as we just saw. using the default approach of re-encoding. And on the x-axis is the date. So we observe that if one does this default approach of re-encoding, then 100% of the cluster IO bandwidth gets consumed for weeks at a time just for this conversion process. This is an acceptable cost of conversion, right? No real system would do redundancy tuning if 100% of the IO bandwidth goes for conversion. So there's a key barrier for redundancy tuning in practice, and to get the benefits of redundancy tuning is being able to do this conversion of already encoded data in a resource efficient manner. So now one natural question that we have to ask here is it even possible to do better than the default approach of re-encoding? And the answer is yes. So let's take a very simple toy example, right? So let's say we want to go from a single parity check code of dimension k to 2k. So I've shown two initial code words here. The empty boxes are data blocks, and the shaded block is the single parity check block. So think of a systematic code. Okay, so now these are the two initial code words, which is a single parity check code of dimension k. And we want to go to a final configuration which looks like this, as shown at the bottom, which has dimension 2k, and it's again a single parity check code. So now here, we can generate the single parity check code for the final code word by only reading the parities of these initial two code words and adding them, right? So that will be the resultant single parity check for the final code word. So the number of blocks that are read here for this conversion process is only 2, because we are reading the two parities. Whereas the default approach of re-encoding would have read 2k blocks, k data blocks from each of the two initial code words. So this is significantly better than the default approach in terms of the amount of number of blocks read. So this motivated us to study code conversion in a more formal way. So before going into the Convertible Codes framework, which provides a means to formally study this code conversion process, so I'll quickly go through some related work. So several other works have considered variants of the code conversion problem, and largely in the framework of regenerating codes. So the regenerating codes was a study of class of codes that optimize for reconstruction of a subset of symbols or blocks unavailable within a code word, as opposed to recovering all the data. So this study was initiated by Demarcus et al., and then there have been very many subsequent works who have looked at bounds and code constructions in this framework. So if one considers the specific conversion scenario of keeping only k fixed and changing n, then increasing n can be viewed as a repair or a recovery process, and then one can leverage regenerating codes framework for that. So, but in today's talk, we will be looking at more formally studying the general code conversion problem, and Convertible Codes is a framework for doing that. Okay, so recall that in code conversion, the goal is to convert data encoded under an NIKI initial code CI into data encoded under a final code CF, and let it be NFKF code. Okay, so we have data encoded under CI, which I'll refer to as the initial configuration, and data encoded under CF, which I'll refer to as the final configuration. And we want to move from initial configuration to the final configuration. So the both codes, CI and CF, are from the same or over the same finite field. And they both encode the same information. So the initial configuration and the final configuration store the same message symbols. That is the same data that is stored. So information stored is the same. They are just encoded differently. Okay, so now In a framework to study code conversion, the first thing that we need to be able to handle is this change in the dimension from Ki to Kf. Now, in order to ensure that we have the same set of message symbols, both in the initial configuration and in the final configuration, we will start with LCM of Ki and Kf message symbols. So let me denote it with capital M. Okay, and let bold M denote this set of message symbols, which is of size LCM, Ki, Kf. This conversion process takes multiple code words in the initial configuration to a different number of multiple code words in the final configuration. So now this is because we have this LCM of Ki, Kf message symbols, right? And then since the dimension K is different in the initial and final configuration, that is Ki and Kf, we are going to have different number of code words in the initial and final configuration. So this need to consider multiple code words, even to capture the smallest instance of the problem, deviates from other problems in the coding theory literature. For example, in the repair efficient codes like regenerating codes or local repair codes, single code word is sufficient to capture the smallest instance of the problem. So, but here, even to capture the essence of this code conversion problem, we need to consider multiple code words. Okay, so we have an IKI code going to an NFKF code, and pictorially, this looks something like this. In the initial configuration, we have M divided by Ki code words. So where M is the LCM of Ki and Kf. And then in the final configuration, we have M divided by Kf code words. So we go from multiple code words under initial code to a different number of multiple code words in the final code. Okay. So now, since we have multiple code words, we need to specify how to partition the message symbols among these different code words. Right? That is basically to say which message symbols are encoded under which code word. So in order to have this information, the Convertible Codes framework has two partition functions. So initial partition, which maps message symbols from M into corresponding initial code words, and final partition in an analogous manner that maps message symbols to the final code words. So let's take an example to digest all this. So suppose we want to go from a 3-2 initial code to CI to a 5-3 final code CF. Here, we will consider 6 message symbols, which is the LCM of Ki, which is 2, and Kf, which is 3. Okay, so let the message symbols M be as shown, A to F. So now, one initial partition function could be as shown here, that is which encodes AB into one code word, CD into one code word, and EF into another code word. And a final partition could be as shown here below, which encodes ABC together and DEF together. Now, if the codes were systematic, then the conversion process would pictorially look something like this, where on the left, we have 3 initial code words. Again, empty boxes are data blocks and shaded blocks are parity blocks, because we are considering the example of a systematic code. And this is under the partition functions that we just saw. And after conversion, we have 2 code words, which are under 5-3 code. And the partition functions are as we just saw in the example. Okay, so now, were there any questions so far? By the way, feel free to stop me anytime if there are any questions. Okay, so now, so far we have this code conversion set up this way, that we have initial code CI with partition function PI, going to final code CF with partition PF. Now, another element that we need in the framework to study conversion is the conversion process itself, which we denote by T. And this conversion process takes as input the set of initial code words and produces the output, which is the corresponding set of final code words, that is, after the conversion process. Okay, now putting all this together, an NI, NF convertible code over finite field FQ is defined as consisting of three key components. One, a pair of codes CI and CF over the finite field FQ, and a pair of partitions PI and PF, which map how the message symbols are encoded under the initial configuration and the final configuration. And we have LCM of KI, KF message symbols. And the conversion process T, which takes as input the initial set of code words and then produces the final set of code words. Okay, so this is a definition for convertible codes. So now the cost of conversion is the cost of this conversion procedure T in this framework. Right? And the goal is to design these elements of this framework so as to minimize the cost of conversion. And we have 3 degrees of freedom in this design process. Right? So we can design the codes CI and CF, we can design the partitions PI and PF, and we can design the conversion procedure T. And this design would be for a given set of parameters NI, KI, and FKF, and also subject to desired decodability constraints on both CI and CF. So this is because both codes, initial code CI and the final code CF, encode data in the storage system at different snapshots of time. So they both have to meet decodability constraints. One example of such decodability constraint could be this maximum-distance-separable or MDS property, which for an NK code would be that any K out of N blocks or any K out of N symbols are sufficient to decode the data. Okay, and then we can also consider various cost metrics, right? So there is access cost, which is basically the number of nodes touched during the conversion process, the network bandwidth, the amount of data transferred during the conversion process, disk IO, the amount of data that is read and written to the disks, and also CPU or the computation costs. So in this talk, I will address only a portion of this design space, and I'll be looking at the space where both initial and final codes are linear and MDS. As far as I know, all storage systems, the codes employed in all storage systems are linear. And also a large fraction of the codes employed in systems today are MDS. And so this linear and MDS is a good assumption to start with. And also, given a very good understanding of the linear and MDS codes in the coding theory literature, this is a good place to start to understand and study the code conversion process. And for cost metrics, I'll be looking at the access cost, which is basically the number of code symbols affected during conversion. By affected, I mean both which is read as well as written. So each symbol that is read from the initial code words and each symbol that is written to in the final code word counts for the access cost because you are touching that node when doing both reading and writing. So access cost is basically a summation of 2 terms. The first one is number of symbols read from the initial code word and the number of symbols written to in the final code. Okay, so in this talk, I'll be looking at linear MDS codes with access cost as the cost metric for conversion process. So in this talk again, I will cover in detail a particular important parameter regime, which we call as merge regime, wherein multiple initial code words are merged or combined into one final code word. We will get into this in detail soon. But I will not be able to cover the general parameter regime. The merge regime that we will look in detail plays an important role in the general parameter regime. And more details about the general parameter regime is available in our ISIT 2020 paper. So in fact, the conference is in the coming week. Right? Okay, so let's get into understanding the merge regime by starting to look at lower bounds on the access cost of code conversion. So as I was just mentioning, merge regime corresponds to combining multiple initial code words into one final code word. So the dimension kf for the final code is some integer lambda times ki. So it's a positive integer greater than or equal to 2 because you're merging more than one initial code words into one final code word. And this lambda corresponds to the number of initial code words merged. Ni and nf can be arbitrary. So pictorially, merge regime would look something like this. So in the initial configuration, we have lambda initial code words. So each of these code words is a code word from Ni Ki code. Right? Again, empty boxes are data blocks and shaded blocks are parity blocks. So it's much easier to think of systematic. Oh, by the way, what I'm going to present today is not restricted to systematic codes. It's applicable in general, but it helps to keep thinking in terms of systematic codes. It's much more intuitive. Okay, so that's the initial configuration, which has lambda code words. And in the final configuration, we just have one code word because this is merge, right? Combining multiple code words into one single final code. And here, this is the final code, which is NF-KF code. Okay, right. So this is the merge regime.
I have
Any questions?
Yeah. And I'm not sure if you already addressed it. So the reason you want to use lambda code word is not because you could, I mean, essentially just use one code word or one stripe. So is it more, it's more beneficial to use all the lambda code words to get one code word? Or each code has a different data here in your figure? The lambda code word, each one is different data, maybe.
Yes. Yeah. Yeah. So let me clarify this. As I was mentioning earlier, so in order to capture the essence of the problem, we necessarily have to consider multiple code words.
Okay.
And that is because Ki is changing, right? K is changing, right? Dimension. And here, each code word is encoding different set of data. Right? And because K is changing, in order to make sure that we have the same set of message symbols both in the initial configuration and final configuration, we have to consider this LCM, Ki, Kf. And if you recall this example, we had A, B, C, D, and EF. So here, if we take that example, we would have 3 initial code words, which is A, B, C, D, and EF. And if it was a merge regime, the final code word would encode A, B, C, D, E, F, all of the message symbols together. Does that answer the question, Sadim?
Yes. Okay,
cool. Thank you. Any other questions? Okay, cool. So this is the merge regime, and this is the regime that we will keep in mind for most of the remaining talk today. Okay, so now I move on to looking at the lower bounds on the access cost of conversion in the merge regime. So I'll introduce an additional notation with this parameter R, which is n minus k. So for the initial configuration, Ri is ni minus ki, and for the final configuration, Rf is nf minus kf. An intuitive way to think about this parameter R is to consider systematic codes again. And if the codes are systematic, then this parameter R corresponds to number of parities. So Ri corresponds to number of parities in the initial configuration, and Rf corresponds to number of parities in the final configuration. And here is the main theorem on lower bound on the access cost of conversion in the merge regime. So for all linear MDS convertible codes in the merge regime, when Rf is less than or equal to Ri and also less than Ki, the access cost is as shown here, which is the sum of two terms. Okay, the first term is the read cost, which is the number of symbols read, and this is lambda times RF, which basically is reading RF symbols from each of the initial code words. So recall that we have lambda initial code words. This is the first term. And the second term is the write cost, and this corresponds to the number of new symbols written. Okay, so recall that the access cost is sum of the symbols read and the sum of symbols written. And if this condition on the left here, if this condition is not met, then the access cost is as shown here, which is again sum of two terms. But this cost is actually the same. If you observe, you'll notice that it's the same as the default approach of re-encoding, because the first term, the read cost, which is lambda times ki, is basically reading all the data blocks from the lambda initial code words. And then you can re-encode and create these new parities, and the RF are the number of parities in the final code word, right? So this is the same cost as the default approach. So basically, you can do better than the default approach when this condition in the first if clause is met. And we will soon deconstruct this condition in the if clause.
Rashmi, to maybe would it make sense to compare it to maybe straightforward scheme where for every new coded bit or symbol, I have to read all the parities in the old code words? So
yes. So in the default approach.
Yeah, so that's the default. So that's where lambda RF plus, no, that would be lambda RI.
That would be lambda ki. So that's this, that is this case. So for example, so you see this lambda ki, right? So ki is the number of data symbols. So and that's the default approach. Yeah. And basically, whenever this condition in the if clause is met, that is when you can do better. And actually, you can do significantly better in scenarios where RF is smaller than ki, right? So basically, instead of lambda ki, there is lambda RF. And if you recall, basically R corresponds to number of parities. And this actually holds true in most real-world storage systems because the overhead of the code used is typically much less than 2. So number of parities is much smaller compared to the value of k. So significant savings, when these conditions are met.
So this is all assuming that you're going to stay in the same field, right?
Yes.
Because I'm thinking maybe if you can, maybe in the new code you operate on a higher field, maybe you can just read just the parities of the old. I don't know, but yeah.
Good thought. Yeah, good thought. Possible. Yeah. So in this first exploration, we have considered the same finite field for both the codes, which is, I would say, a good assumption in storage systems because often you have a set finite field and then you're operating using those. But that doesn't. But that doesn't mean to say that you cannot have different field sizes. I think it is a very valid direction if one can get even more savings by doing that.
Because again, I don't want to keep delaying, but imagine one of the parity is just a simple parity check. All I have to do is just read the parity. I don't even need to read what you have lambda. So I don't have to read the systematic. I can just add them.
Yeah. So that was a toy example that I gave earlier, right?
Oh, I missed it then.
Right.
Okay.
Yes. So you can do that, and in fact, as you will see, the explicit constructions that I'll talk about, the simplest case of that explicit construction would be something like that. If it is a single parity check code, yes, one can do that. But even there, the finite field is remaining the same, right? So
the reason if it's not parity, then you may cancel out things and won't be MDS anymore. And this is why I was thinking maybe you need a higher field, but yeah.
So in this, you don't need though. Yeah. So what I was thinking was, if by going to a different field, if even more savings is possible, then I think it would be a very valid direction to explore. Yeah. Okay, cool. Yeah, so basically coming back, so we have this lower bound on the access cost of conversion for all linear MDS convertible codes in the merge regime. That is, as we saw, when this condition in this if clause is met, then the access cost is as shown here on the right, which is sum of the number of symbols read and written. And when this condition is not met, then you cannot do better than the default approach. Okay, so now I will quickly sketch the proof for this result. So before doing that, I'll introduce some notation. So we will call symbols as unchanged symbols if those symbols are from the initial code words and that remain as is even in the final code word. That is, you can think of this as symbols or blocks that were there in the initial configuration and also will continue to be there in the final configuration. That is, they are not modified. And I'll call symbols as new symbols if those symbols were not present in the initial code word, but they are present in the final code word. So basically, new symbols are the ones that would be generated using the data that is read from the initial code words, and they would be written to in the final code word. Okay. So now the proof involves 4 steps, and I'll quickly walk through them. So the first step is on the equivalence of the partition functions. So in the merge regime, and specifically in the merge regime, all possible pairs of partitions functions, this PI and PF, are equivalent up to relabeling. So this is because, recall that in the merge regime, we are combining all the initial code words into one final code word, right? So the way the message symbols are mapped to different initial code words doesn't have an impact. So basically, in the merge regime, we do not need to specify the partition functions. And I want to highlight here that this is specifically for the merge regime. And in fact, when we go to the general parameter regimes, it turns out that carefully designing the partition functions is critical. And as we show in our ISIT 2020 paper. But for the merge regime that we are focusing on in this today's talk, we do not have to specify the partition functions. Okay, now the second step is we upper bound the maximum number of unchanged symbols. So recall that unchanged symbols are symbols that remain as is, as in the initial configuration to the final configuration. So they are there in the initial code words as well. It remains in the final code word as well. So you can see intuitively why we would want to upper bound the maximum number of unchanged symbols, because more the number of unchanged symbols, right, the less that we have to write, because only new symbols need to be written. And potentially, since we have less to write, we have less to read as well, because less to create new, right? So an understanding of an upper bound on the maximum number of unchanged symbols is useful. And here is the proposition on that. So in any linear MDS convertible code in the merge regime, there can be at most ki unchanged symbols from each of the initial code words. So this result directly follows from the MDS property. So basically, from each initial code word, we cannot have more than ki unchanged symbols. So based on this, we define convertible codes as being stable if they have exactly ki unchanged symbols from each of the lambda code words. That is, in total, they have exactly lambda ki unchanged symbols. So recall that R is n minus k, right? And in this merge regime, when we are merging lambda initial code words, kf, that is the dimension k of the final code, is lambda times ki. And R in the final configuration, which is RF, which is n minus k, where k is lambda ki now in the final configuration. So basically, if lambda ki symbols are remaining unchanged, we are only left with RF symbols that can be new, right, in the final configuration. So basically, in stable convertible codes, there are exactly lambda ki unchanged symbols, which means that there are exactly RF new symbols. Okay, so stable convertible code. So this will be important when we go to the next step. Please feel free to ask me any questions if you have here. Okay, so I'll move on to the next step. So in this step, we lower bound the access cost of conversion for linear MDS stable convertible codes. That is, we restrict our attention to stable codes in this step. So recall that as we just saw, stable codes have exactly RF new symbols, right? So which means that the number of symbols returned is fixed, which is RF. So the only thing that needs to be quantified now in order to quantify the access cost is the number of symbols read from the initial code words. And here is the lemma for this step. So in any linear MDS stable convertible code in the merge regime, one must read at least min of these two terms, that is ki and RF symbols, from each of the initial code word. Okay, so we will come back to this. And if RF is greater than RI, that is, if you're thinking about systematic codes, then if number of parities in the final configuration is greater than the number of parities in the initial configuration, then one must read ki symbols from each of the initial code word. Okay, so basically, the second clause is saying you have to read all ki symbols from each of the initial code word, which is basically same as default, right? So now let's go back to the first clause, which is where you can have benefits over the default approach, right? So this, if you look at this, the amount of read, which is min of ki and RF. So again, recall that default approach is sufficient if you have to read ki, right? Now, if you have to do better than default, you want RF to be the min here. So basically, in order to be better than the default approach, you want RF to be smaller than ki. So this was one of the conditions in the theorem, right? So in the theorem, if you recall, we had two clauses, and this is one of the clauses where it comes from. And then if we now look at the second condition, here again, if RF is greater than RI, we are no better than default, right? Because you have to read ki symbols from each initial code word. And hence, you need RF to be smaller than or equal to RI as well in order to do better than default. And this is the second condition that was there in the theorem. So I'll not go into the proof of this lemma here. And instead, I'll move on to the fourth step, which is to remove this stability restriction. So recall that step 3 was bounding the access cost only for stable convertible codes. And in step 4, we remove that restriction by showing that basically all convertible codes that are not stable necessarily have higher access cost. So, and here is the lemma, which states that all access optimal linear MDS convertible codes in the merge regime are stable. So basically, it suffices to consider only stable convertible codes. And hence, the result that we saw in step 3 is applicable for all and not limited to only stable codes. Okay, so putting this all together gives us the theorem that we saw earlier. There's bounding, providing a lower bound on the access cost of conversion in the merge regime. Okay, so now we saw the lower bound, and this turns out this lower bound is achievable. And I'll present this achievability via an explicit construction. So this explicit construction is applicable for all parameters in the merge regime, and the construction is also systematic. So recall that the first case, in the theorem we have two cases, and the case when RF is greater than RI or RF is greater than or equal to KI is trivial because one cannot do better than default approach. So the interesting scenario is when RF is less than or equal to min of both Ri and Ki. And this is where we can do significantly better than the default approach. So in this case, let G represent the generator matrix for the code that I'm going to present. Gi corresponds to the initial code Ci, and Gf corresponds to the final code Cf. And recall that I mentioned that the construction is systematic, and hence the generator matrix has this form IP, right? P corresponds to the parity symbols. And note that PF here, the matrix P corresponding to the final code, is lambda times taller than Pi. So now for this construction, so I'll first present some structural properties that the code should satisfy in order to be access optimal convertible code, and then present an explicit construction for these matrices that meet these structural properties, and hence the construction will be access optimal. Okay, so the first property is a well-known property on MDS codes, which is basically says that this matrix P needs to be super regular in order for code C to be MDS. That is, every square submatrix of this matrix P of the generator matrix needs to be non-singular, right? So now, in order to be MDS, hence we need both Pi and PF to be super regular. Now that is property one. Now the second property relates to the code conversion process. So here, this property is what we call as T-column block constructible. So before going into this, so I'll go into a simpler property, which is T-column constructible. So we call a matrix M1 T-column constructible from another matrix M2 if and only if there exists subset of columns of M2 that can span columns of M1. That is basically using a subset of size T of columns of M2, we can generate all the columns of M1. Okay, so now using this T-column constructible property, now I'll build up onto T-column block constructible property. So we'll call a matrix M1, now it's a taller matrix, lambda times taller matrix, is T-column block constructible from a shorter matrix M2 if some condition holds. And before going into that condition, I want to pictorially just show you here that M1 is a tall matrix and M2 is a short matrix. And the condition is as follows. So this is if and only if every submatrix of M1, which is of height M2, which is row-wise block submatrices, are spanned by M2. Okay, so now let's see why this relates to the code conversion property. Right? So recall that for the access optimal linear MDS convertible codes in the merge regime, so recall that the read cost from each of the initial code words was RF. So what this means is that it is sufficient if PF is RF column block constructible from PI. Then we will be able to generate the RF new symbols in the final code word by reading only RF symbols from each of the initial code word. Okay, so basically the theorem is the following. So these are the two structural properties that a code should meet in order to be access optimal convertible code. Right? PI and PF are super regular, and PF is RF column block constructible. So Salim, just a quick question. So I want to make sure we're okay on time. So what would be a...
So maybe we still have 5 more minutes.
5 more minutes? Okay, sure. Yeah, so I will go through the remaining part quickly and probably skip some details. Okay, so basically, I'll quickly show you how the construction looks like. So let F be a finite field of size 2 to the D, and D is going to be, we're going to make it very large very soon. And let theta be the primitive element in this finite field. Recall, we have this generator matrix in this IP form, and the matrices in our constructions look something like this. So basically, each ijth element, both in PI and PF, are of the form theta to the power I-1 times J-1. Okay, so I'll just quickly go through an example to see why this works. So let's say we want to go from a 6.3 code to a 9.6 code. So in this example, both Ri and Rf are 3, right? And if you're thinking systematic, there are 3 parities in both. And Pi and Pf in the constructions look like this as shown on the left. Now the conversion process looks as shown on the right, where the data blocks are not touched at all, and the new parity blocks are generated using some linear combination of the existing parities, and the linear combinations are defined based on some appropriate powers of theta. Okay, and we can show that this above constructions, this construction yields access optimal linear MDS convertible codes for all parameter values in the merge regime. And the proof basically is to show those 2 structural properties that I established hold true for this construction of Pi and Pf. So the superregularity property comes from the fact that we make the field size large. And hence, this is not a practical construction. So this is mainly for showing achievability. Okay, and very, very quickly, we do have some low field size constructions. I'll not go too much into the details, but the key idea is to pick the matrices Pi and Pf from a specially constructed triangular array, which is of this form. Okay, so here, this BIs need not be distinct. And you can see that this triangular array has this structure where if you go from the bottom left to top right, the elements are identical. So this form is called as a Hankel form. And we can use this Hankel triangular array to construct the matrices Pi and Pf in such a way that the 2 structural properties that I mentioned holds. So I'll just quickly flash this example where we're going from 9.5 code to a 12.10 code, where Ri is 4 and Rf is 2. So basically, we pick the P matrix for the initial code as the first 2 columns of this triangular array, because for PF, okay, so the final code. So that's because Rf is 2, right? So PF has 2 columns, so we pick that as the first 2 columns. And since Ri is 4, so we need to pick 4 columns for Pi, and those are as shown here. So these 2 and these 2. Okay, so we pick in this form. So now we can see that PF is 2-column block constructible from Pi, right? Because you can see that we can stack this part of Pi down here, and that makes PF, right? So just because of this, by design of this Hankel array, this block constructible property holds. And the field size for this construction is, here it is NF minus 1, which is 11 for this example. Okay, so recall that these were the 2 structural properties that had to be satisfied, and by design, the first column, RF column block constructible property holds. As we saw, we can just stack Pi to form PF. And in order to make sure that Pi and Pf are super regular, we will impose an additional constraint that every submatrix of Pi and Pf are super regular. And it turns out there exist algorithms to construct such super regular Hankel arrays. And this work was done in the context of constructing specific MDS codes. Okay, so this construction leads to a sequence of convertible codes, which is parameterized by S. And so this is a parameter that provides a trade-off between field size and the parameter regime. So this doesn't cover all the parameter regimes. So this covers only some specific parameter regimes, and I'll not go into the details here, but details are available in the paper. Okay, so now this was all merge regime, and as I mentioned earlier, I'll not be going into the general regime here, but when towards going into general regime, there is another important parameter regime called the split regime which is, you can think of it as an opposite to merge regime, which takes one code word in the initial configuration and splits it into multiple code words in the final configuration. So it looks something like this. So exactly the mirror image of merge, so split. And in order to analyze and construct codes for general parameter regimes, we use both merge and the split regimes and their generalizations. And using this, we can cover all the parameter regimes. And as I mentioned earlier, it turns out that for the general parameter regimes, you have to carefully design the initial and partition functions as well. And we have lower bounds and explicit optimal constructions in the ISIT paper, the ISIT 2020 work. Okay, so in summary, doing redundancy tuning in storage systems in a manner that is aware of heterogeneity of failure rates in storage systems has the potential to provide significant cost and energy savings. However, a key challenge in practical adoption of redundancy tuning and reaping these benefits is resource-efficient conversion of already encoded data. So I presented Convertible Codes, which is a framework to formally study this code conversion process. And I also presented tight lower bounds on a specific cost metrics, that is the access cost of conversion for linear MDS convertible codes. So I also presented matching explicit constructions for all parameters, which however had a high field size. And I also presented low field size explicit constructions for certain parameter regimes. So in this study, we have just scratched the surface of studying code conversions and convertible code constructions. There are many open problems. So first of all, as I mentioned, the low field size constructions that we have for access optimal convertible codes does not cover all parameters. It's only for specific parameter regimes. And the achievability construction that we have that works for all parameters is very high field size. So that is not practical. So it remains open to design low field size access optimal convertible codes for all parameter regimes. And also, so it is interesting to think about designing convertible codes that are simultaneously optimal for multiple final parameters. So as you can imagine, in many cases, you might not know the final parameters. Interestingly, it turns out that the constructions that I presented are optimal not only for one specific value of the final code parameters, NF and KF, that presented for, but it turns out that they are optimal for multiple values. But it would be interesting to do a more formal study of how one can design such codes by design, that they are optimal by design for multiple values of final parameters. And also, so we so far have looked at mainly the access cost of conversion in the work that I presented today. As I mentioned earlier, it would be of interest to optimize other metrics of cost conversion, including network bandwidth, the computation of the CPU, and the disk IO. And we have some interesting preliminary results on the network bandwidth side. That looks exciting, but even the other costs are of interest in the real world storage systems. Okay, with that, thanks a lot for your attention, and I'd be happy to take any questions.
Thanks a lot, Rashmi. So maybe I'll ask a quick question in case in the meantime someone else has a question. I'll also upload. So here's my upload.
Sure, yeah. Thank you. Yeah.
I was thinking that there has been some work on kind of mixed code between local. You want some parities to be local and some parities to be global.
Yeah.
And I feel that this convertible code that you have, let's take the systematic and throw in the old parity and throw in the new parities. So the old parities are the local parities, and the so have you thought of or are there some connection, or can you go back and forward in terms of constructions or?
So I'm aware of the work that you're mentioning, that where there are both local parities and global parities. Yeah. But basically, in the problem setting of convertible codes, basically you would be having only one of the two, right? So basically you would have, let's say we are going something like merge, in which case in the initial configuration you will have only local parities, right? And in the final configuration you'll be only having the global parities.
So if I know that I'm gonna merge and I know the parameters, maybe I can already like rig up the code such that I know I'm gonna merge. Maybe I don't know. So
yes. Yeah. No, precisely. That's how the design process works. But basically, what you're suggesting works in scenarios where this, where it can be cast as a repair problem, right? So as I was mentioning earlier, so if one simple example would be if you keep k fixed and then if you're increasing n, then you can in some of the works which including myself have worked on earlier in regenerating codes, that basically there we pretend that the parity was already there, right? And then when you're generating, you can think of it as a repair problem. Yeah, and similarly, as you mentioned in the setting that you talked about, where there are some local and some global parities. Yes, so there could be some specific parameter conversion processes where it could be mapped to those set of parameters. Yes, yeah, I agree. Yeah. So our goal here was basically to be able to study general set of parameters. So given any ni ki, we should be able to go to any nf kf.
I don't know if we have one more question.
Yeah, I do have a quick question.
Yeah.
So thanks very much for the very nice talk. So this PF and PI matrix that you use, the primitive element data from the field.
Yeah.
So those matrices were van der Waals matrices, basically.
Yeah.
What you showed there. Yeah. So you said that for a very large field size, then they're going to be super regular. But we know that van der Waals matrices basically, in general, they're not, of course, super regular.
Right.
And so here, what do? I mean, basically, you go over all the square submatrices and you look at the determinant as a polynomial and you pick the largest degree, and right? That's what you need to do.
That's the typical argument that is used to show superregularity, and then So that's why the field size there is large.
I see. And the Hankel construction it looks like a generalized type of Cauchy matrix, right? Are they related?
Generalized what?
Cauchy matrix. Cauchy matrices are all super regular, right? And
Cauchy matrices basically can be used as the P matrix for constructing MDS cores, right?
Sure.
Here also, these Hankel arrays were also originally, proposed for constructing MDS cores having some properties.
Mm-hmm.
So in that respect, yes, but there could be more connections.
Okay. Right.
In the moment, I don't recall. Yeah. Yeah,
Sure.
but I think it is possible because both of them have been, kind of designed for constructing this P matrix for MDS cores, right?
Sure. Especially not only MDS, I believe that this superregularity is something beyond MDS, right? And I think that Cauchy is one of the few matrices that are well structured, and they have, and perhaps this Hankel, I suspect that there might be some connection between these two.
That's true. Yes.
Okay, thank you.
All right, thank you everyone. Thank you, Rashmi, and everyone. I hope you have a good summer and enjoy ISIT next week. And I'll see everyone in September, unless we have something in the meantime. You'll get updates through the emails.
Yeah. Okay. Yeah. Thank you, everyone. Thanks, Salim, and I hope I'll see some of you virtually during ISIT.
Thank you. Bye-bye.
Bye. Thank you.
Bye.